Hello everyone, welcome back to another lesson. Today's learning goal is I can compare and contrast association and causation in real-world problems. I can calculate the correlation coefficient between two quantitative variables using technology, and I can interpret the correlation coefficient as a measure of the strength of the linear association. Those are a lot of big words. So let's start off with association, causation. Okay, we're going to talk about those. And then we're going to do the second one in class, okay, which means you will need to use or have your calculator with you tomorrow. And we're also going to talk about the interpreting of what is called a correlation coefficient. So let's go ahead and get started. Scatter plots are graphs that use points to display relationships between two sets of numerical data and can be useful for observing trends, patterns, or associations between two variables. Okay. If the overall shape of the data resembles a line, the association is described as a linear. Okay. So, scatter plots may display the following types of association. Okay. So here, as the value of x increases, the value of y here seems to increase. And here we have our studied and exam score. Okay, so as more you study, it seems that you seem to get higher scores as you do so. Here, and this is called a positive correlation. The more you do, the more you get. Okay, here it says sweater sales and snow cone sales. Okay, so it seems as the more snow cones are sold, the fewer sweaters are sold. Okay, because we have a negative. Okay, that slope of a line that would go through here would seem to be negative. So as the value of x increases, the value of y decreases. No association. Okay. So this is positive association, negative association. No association means that the change in one variable doesn't seem to have any effect on the other. So you can see that these are all over the place. There doesn't seem to be a trend with any of these dots. Here, causation exists between two variables that change in one. Causation exists between two variables when the change in one variable causes the change in the other. Okay. Describe which of the scatter plots above displays causation. So here, sweater sales and snow cone sales, they don't have any reason for the snow cone sales to affect the sweater sales. Here, though, our studies seems to increase exam scores, which makes sense. So there should be a causation between that. Our studies causes you to have a greater grade on the exam. So the positive example displays causation because the number of hours studies causes the exam score to change. As opposed to sweaters and sales and snow cone sales, there's no reason to think that snow cone sales would affect sweater sales. And there's no reason to think a person's age affects pairs of socks owned. For each of the variables, a pair of variables in the table below, describe the association and whether you expect there to be causation between the variables. So as the number of cars in a restaurant parking lot increases, the number of available seats inside the restaurant decreases. Well, it seems that there is an association in this. There should be a negative association, right? As the parking lot increases, the number of available seats decreases, so that should be a negative association. And is there a causation for this? Well, it makes sense because the more people there are parking in the parking lot, the more people there's going to be inside the restaurant. As your height each year since the birth increases, the average annual price of gas increases. Is there an association? Yes, both of them are increasing, so this is going to be a positive association. Is there a causation? Well, your age does not affect the gas prices, so there is no causation. Both plots at the right display a positive association. Predict which has a stronger association. Explain your thinking. So here, this one looks like it has an upward trend, and so does this one. But if you see that these dots are closer to a theoretical line that could go through here, as opposed to A, the theoretical line would go through probably like right here, but the dots are further away from each other from that line. So therefore, B, because its points are closer together and shaped more like a line. Association can also be referred to as correlation. Okay? The more points are spread or scattered, the weaker the linear correlation. The closer the points are to one another in the shape of a line, the stronger the linear correlation. So back here, A has a weaker correlation compared to B. So again, correlation, weaker. The closer the points are to one another, the shape of the line, the stronger the linear correlation. The correlation coefficient, known as R, so it's often represented by the letter R, is a value between -1 and 1, used to measure the direction and strength of a linear scattered plot. So here, we talk about a strong negative association or correlation. Okay, the closer the number is to -1, it's a stronger negative correlation, which again, a downward trend. Here, between let's say -0.5 and 0 is a weak negative correlation. 0 to 0.5 is a weak positive, which means it goes upward. Okay, and here from 0.5 to 1 represents a strong positive correlation. Okay, and we'll learn how to calculate this using our calculators tomorrow. But here it says the 4 scattered plots shown have a negative coefficient listed on the cards below. Or excuse me, have a correlation coefficients listed in the cards below. Based on the information above, write the value of R underneath its corresponding graph. Okay, so we have A and C are negatives, so it's going to be either -0.9 or -0.5. Okay, so A and C has a stronger negative correlation because these dots fit more like a straight line than this one. So therefore, this is going to be the -0.9. And this one's going to be the -0.5. B and D are both positive correlations. So these two, this one is going to have a stronger positive correlation, okay, because it looks more like a line, so it's going to be 0.8, while this one is going to be 0.2.